For each of the polygons formed by algebra tiles below, you're supposed to sketch and label the shape on your paper and write an expression that represents the perimeter. And then finally, you're supposed to take that perimeter expression and simplify it as much as possible. So I know I've got unfair advantage here. I've already got this, and I'm just writing right on this page, so I don't have to write it down. But follow along, please, right? The dimensions of these, right? This X tile has a dimension of 1 by X, so that's X units long. This is a 1 by 1 tile, so that's a dimension of 1. This is a Y tile, it's Y times 1, so this is Y units long. Then I've got another 1, and then I've got an X. Up and down here, this has to be 1 unit. And then down below, this is an X, a 1, a Y, a 1, and then finally an X. So if I go through and I add all those up, right, I guess I could say, hey, I'm going to start, I'll do this with green. I'm going to start here and go this way. So when I do that, just writing those down, I've got X plus 1 plus Y plus 1 plus X plus 1 plus another X plus a 1 plus a Y plus a 1 plus an X, and then finally plus 1. So that was much larger than I anticipated it being. So if I go through and I just combine all of my like terms here, I've got an X, an X, an X, and an X. So there are exactly 4 X's when I simplify this. If I do the same thing for Y's, you can see here's 1, 2. There's only 2 Y's, and I could see it in the original diagram. So plus 2 Y's. And then finally, all of my 1's, I've got 1, 2, 3, 4, 5, and 6. So we'd have plus 6. So the simplest form for this expression for the perimeter is 4x plus 2y, and then plus an awful looking weird 6. Let's do the same thing for part B. Let me clear the screen here. So for B, a little bit trickier because I've got some parts that are kind of overlapping here. But definitely part of this is an x by 1, right? And this up here is a 1. This would have to be a 1 and a 1 and a 1. Now this next part, I'm going to highlight it in green. That part is not x, right? And it's not 1 either. What is it? Well, if you look at it, right, it's an x, but then we're subtracting a 1 from it. So this part right here in green is literally that x tile, but then we're taking away a 1 from it. So that's the length of that piece. So if I go ahead and combine those pieces, you can see, I guess I'll start with the 1 on the top and I'll go this direction. I've got a 1 plus an x plus a 1 plus a 1 plus a 1. How many ones is that? It's one. It's a 1. I'm losing track of things here. I've got a 1, 2, 3, 4 ones, right? 1, 2, 3, 4 ones. 1, 2, 3, 4 ones. And then I've got a plus an x minus 1, and that's everything. That looks awful. If I combine those, my like terms, there are 2 x's involved, and I can see those 2 x's. So I've got a 2x. And then in terms of the ones, if I count them closely, right, there's a 1, 2, 3, 4, 5. And then this is a negative 1, right? So if you look at it, I've got a plus a 5 and then a minus 1. So let me do this down on the picture too, because I might have messed up. 1, 2, 3, 4, 5. Yep, that's right. And then I've got the minus 1. So if I simplify that one step further, right, this is 2x and then plus the number 4. So this is the perimeter for part B, as simplified as possible. Wow, definitely some more complexity here in terms of overlapping shapes. The first tile I have here that I'm noticing is a y squared tile. Well, in order to get a y squared tile, you need to have a y by another y. The next tile there is an x times y tile. Well, if this is the dimension y, this has to be the dimension x. And then you can see there are some legitimate 1 tiles, right? I've got a 1, and a 1. And this is a 1, and a 1. And then I've got a 1, and a 1. So there's quite a few 1s. Now again, like that previous problem, there's some weird overlap things here. So if you look at this piece right here that I'm marking in this kind of blue color, right? That's the whole thing is x long, but I don't have the whole x. I have an x take away a 1, right? So this piece in blue is equal to x subtract 1. So that's what this blue piece is. And the other piece over here is kind of similar, right? I've got this yellow piece, which it would be y, but it's not y because I've taken away a couple ones from it. You see, I've taken away a 1 here, and I've taken away a 1 on this side. So what I'm left with here is this is a y minus 2. That's y minus 2. Well, let's see if I can write this a little bit more simply than last time. So if I look at this, just my pure y's by themselves, I have 3 of them, right? I have 1, 2, 3 y's, so I'll write a 3y, and then plus. In terms of pure x's, a whole x rather, I have 1 of those plus a whole x. And then let's count up the units I have. I have got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got a plus 9. And then I need to add this yellowy piece, right, which is a plus y minus 2. And then I have this blue xy piece, which is plus x and then minus 1. Now we can definitely simplify that by collecting some like terms. So you can see, for example, I could collect up this x and this x, and we could also collect the y's and the 3 y's here. And then the other thing we could collect up, and I guess I'll use a different color for that, is I've got a plus 9, a minus 2, and a minus 1. So if I collect those like terms, 3y plus a y would make 4 y's in total. And then my x's, I've got plus an x plus another x, which is plus 2x. And then finally my numbers, I've got 9 minus 2, which is 7, and 7 minus 1, which is plus the number 6. So this is the expression for the perimeter that is simplified as much as possible. And I got excited and I hit stop recording before I did D, so I've inserted another slide to do part D here. So similar technique, right? This dimension is a y tile, so it's a y by 1, and then I've got another 1 and a 1. This is an x. Down here I've got a 1. This is x units long. This is x units long. Up here I've got a 1 and a 1 and a 1. This piece right here is pretty freaky, right? If you look at that, what's going on is it starts with y, and then it subtracts 2 things, right? One of the things that it subtracts is this 1 right here, and the other thing that it subtracts, and I'll mark this in green, is an x tile. So think about what I'm saying here. I'm saying, hey, this piece is y units long, but you have to subtract an x, and you also have to subtract a 1. So it's y minus x minus 1. So that's the length of this little piece right in here. So if we go ahead and put together the other pieces we have here, let's go ahead and just combine them. So I've got, you can see I've got a y plus, let's see, I've got 1, 2, 3 x's, so plus 3 x's. And then in terms of units, I've got 1, 2, 3, 4, 5, 6, 7, plus 7 units. And then I've got this plus y minus x minus 1. So we can definitely simplify that a bit further. You can see that I've got a y and I've got another y. I've also got 3 x's, and I need to subtract an x. And the other thing that's going on here is I have a 7, and I need to subtract a 1. So when I combine my y's, y plus another y is 2y, and then I've got 3x minus an x, which is plus 2x, and I've got 7 minus 1, which is plus 6. So this is the perimeter of this shape, as simplified as much as possible. Use what you know about slope and y-intercept to graph y equals -1/2 x plus 3. So I'm just looking at it and using my information about slope and y-intercept. For this particular equation, I have a slope pattern of down 1 unit, right? Down 1 unit. and then to the right 2 units, right? That's why it's -1 over 2. And this has a y-intercept that's located at 3. So this is where I'm beginning. So if I want, I could grab my pen. Let's get a slightly thicker pen here. And I'll use the same color, but I'm going to start right here at +3. That's where I'm beginning. And from here, I'm going to go down a unit and then 2 to the right, down 1, 2 to the right, down 1, 2 to the right. And at a certain point, you're like, hey, with consistency, I know exactly what this line's doing. So at that point, don't leave it like this. Grab a ruler and take your ruler and line it up with those points as best you can. And then go ahead and just draw the line that goes through those points. And of course, always put some arrows there because we're indicating that this line is an infinite object. It never stops. It goes forever in both directions. But that's the graph of that line, and I graphed it using the fact that this value right here is my y-intercept, and this was my slope pattern down 1 over 2. Well, this keeps coming up. We've seen this in several other homework problems in the past. It says write the equation of the line containing the points given in the table below. So let's go ahead and take a look at it. One of the things that I don't see here is they've used the function notation f of x, but this is equivalent to y, so I can think about these right here when I'm looking at the change in my y values. So if I look at change in x, right, this increased, it went up by 2 units, and my y value increased by only 1 unit. It was +1 unit, right? 2 to 3 is 1. If I go from 3 to 4, that's an increase of 1 unit. 4 to 5 is an increase of just 1 unit. For 4 to 6, 4, 5, 6, that's 2 units. Whoops, 2 units, not 5 units. And 6, 7, 8, that's again going up by 2 units. So each time I have a change in y, and remember, those are recorded on this bottom table here, so be careful. The change in my y's are 1 in this case, and the change in my x values, x's are going up by 2 each time. So the slope of this line that I'm looking for, the slope is equal to 1/2, which is important. That's one of the 2 parameters we need to define a line in slope-intercept form, the slope, and then the other one's the y-intercept. Now that I know the slope, I'll go ahead and use any one of these points. It doesn't matter which one. We'll go ahead and use this one because it's nice. It's 2 and 2. They're the same numbers. So you can see for these 2 points, we've got an x value and we've got a y value. And we also have our slope, which we usually denote with the letter m. So let's go ahead and write down our slope-intercept form of equation. Oops. So we've got y equals m times x plus b. Our y value in this case was 2. Our slope was 1/2, and our x value was 2, and then we've got the plus b. If I simplify this, 1/2 times 2 is 1, so I've got 2 equals 1 plus b, and if I take away 1 from both sides, you can see that we can conclude our y-intercept b is +1. Well, now that I know what my y-intercept is, and now that I know what my slope is, I can write the equation of this line, right? The equation is y equals 1/2 times x, and then plus 1. The next question says, in problems 78 and 79, which function had a greater y-intercept? How do you know? Well, if I take a look at these, I think this was problem 78, right? And this was problem 79. And remember, the y-intercepts occur when x is 0. And if you think about that more broadly, right, anytime you've got your Cartesian coordinate plane, if x, right, over here, this is the way for positive x's, and back this way we have our negative x's. So right here on this particular line called the y-axis, all of our x's are exactly 0, right? We call this the y-axis, and it is, but it's also the line x's are all equal to 0. So if I look at this, right, for 78, if I put in x is 0, I have a y-intercept at 1, 2, 3. So here's my y-intercept for that first problem for 78. And if I put in 0 for 79, right, my y-intercept is at 1. So clearly it says which one has a greater y-intercept. The first one had a greater y-intercept, right? It was at 3. And 3 is definitely above the number 1. So for question 81, most of these items I could do just fine on a normal piece of graph paper, but A is something I definitely would want to do with a piece of patty paper perhaps, so that I could be real precise. I would pretty much trace this shape on the patty paper. I would place a small dot at the origin on the patty paper, and then I go ahead and go through a 90-degree rotation. I'd probably make sure that, this line eventually lined up with this one. Because it does say go counterclockwise. Now, I've set this up in GeoGebra because I can show that probably easier online than I could with patty paper. But if I take this object and I go through a rotation, right? So I'm just rotating about the origin. Oh, and it's gone off the screen there. But when I do that, you can see all these points go to their new locations. And the one point that they're asking me to do is it says record the coordinates of point CC prime. And I can see this is CC prime. I'm sorry, this is C prime rather. So from C to C prime. Notice that C had the coordinates -1, +5, right? -1, +5. C is going to -5, -1. Interesting, I think, right? This was -1, +5, and this is -5, -1. Something similar is happening with B, right? B was at -1, +2, and B prime ends up going to -2, -1. So something definitely worth writing down there to see. But the rest of the transformations, I can do without using GeoGebra or patty paper, but I definitely wanted to get this one out of the way first. So we saw it happen on the last slide. Let's go ahead and just write down the result there. So for question A, the point C, which was located at, it was at -1, 5, goes to C prime, which was located at, let's see, when I brought this around, this right here was where C primed was, which was located at -5, -1. So you can see what happens. It looks like the X value just moves to where Y is. So if I was going to try and write some rule for a 90-degree, what is this? This is counterclockwise rotation. It looks like the rule might look like this. You take your X, Y, and what happens first of all is your X just goes to where Y is. And you can see that's what happened, right? Y was at -1. I'm sorry, X was -1, and that went to where Y was. And the other thing that appears to happen is my Y value goes to where X is, except it changes sign. So maybe it becomes the opposite of X. So this is way beyond the scope of this problem. I'm not asking you to do that right now. The big thing I want to see is, can you, use patty paper or something to visualize this transformation. But I believe that this is a rule that will basically rotate the entire Cartesian coordinate plane 90 degrees counterclockwise. And I'm coming up with that just by observing just a few points here. So the next thing it does say to do in part B, it says reflect rectangle ABCD across the vertical line x equals 1. So that vertical line, let's see, this line is right here. I'll just draw this in green. This is the line x equals 1. And if you look at it, right, the y values are changing, right? Way up here, y is at 6. Down here, y is at -2, y is at -4. But what's not changing is x. X's are always negative or +1, or they're always at least intended to be +1. So if I was going to reflect this across that line, right, basically what would happen is C prime, it's 2 units away, it would go exactly to this spot. So this is now C prime. B prime would be right exactly here. Here's B prime. A prime, let's see, that's 1, 2, 3, 4 units away. 1, 2, 3, 4 units away from B. So this should be A prime. And then D prime would be right here. And that's 1, 2, 3, 4. Yeah. So what happens when I reflect across this line, right? I get this new rectangle, and here are all the points. And this question is just asking me, hey, what are the coordinates of C double prime? By the way, this came up in class, and someone else in the class, not me, was correct. Even though we're always going back to our base figure, they are calling this C double prime. And I think I incorrectly said, well, maybe this would be C prime, but they're using the double primes even though it's just one transformation from the original shape. So where is C double prime at? C double prime is at, double prime, right, is at the coordinates 3, 5. So it's at 3, 5. All right, I guess that's it for part B. So part C says translate the entire rectangle ABCD so that C is moved 5 units down and 12 units to the right. So for each one of these, we're going to do that. So if I'm going to move down 5 units, that's 1, 2, 3, 4, 5. And then I'm going to go 12 units to the right. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And yeah, I know that's 11, but the reason why I'm calling it 12 is this is the 12th one over because I was starting at -1 over there. So that is down 5 over 12. So this point then becomes the new C, and at this point we're actually up to C triple prime. So that's where C triple prime would go. And you could figure out everything else from there, right? The next one would be down 3 right here. This should be B triple prime. And then if I went back 1, 2, 3, 4, this should be my A triple prime. And then right up above here on this line is D. Whoops, not C, D, and then triple prime. So every single one of those is being subjected to this shift down 5 units and then 12 units to the right. And this is the resulting rectangle once that happens. Let's see, it says, how is this transformation related to the line y equals -5/12 x plus 1? Well, if I was to think about that line, plus 1 is the y-intercept for that line. It says down 5 over 12. 1, 2, 3, 4, 5, and then over 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. So I think I see what's happening here. If I think about that line, it does have a y-intercept of 1, and it is down 5 units over 12 units. What's interesting about that is if I was to draw any of the lines from, like, for example, the line from C to C triple prime, actually, from C to C triple prime, and if I was to draw the line through D to D triple prime, this line right here, and I could do the same thing with B to B triple prime, what ends up happening is all of these lines have the exact same slope of down 5 over 12. So they're all parallel to each other. So I would say this translation of this shape down 5 over 12 units, all of those lines that connect those is parallel to the line y equals -5/12 x plus 1 because it's down 12 over 5. And then finally it asks, what's the area of rectangle ABCD? Well, that seems pretty straightforward, right? If I look at this, I'll use this blue color. This is 1, 2, 3. So one of my dimensions is 3. And then along here I've got 1, 2, 3, 4. So it's 3 by 4. So this is exactly 12 units, 12 square units. And you see them right there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's exactly 12 units squared is the area. And again, what I said for C was that the transformation is parallel to that line, y equals -5/12 x, -5/12 x plus 1, because all of them have that down 5 over 12. Okay, this has admittedly been kind of a longer homework assignment. Maybe it's just me, I don't know. So 82 says, interpret each of the following effects on the function f of x. Now, they don't define the function at all. They're just saying, hey, you've got some function f of x. And for example, what would it look like if you were to do f of x plus 2? Now, here's what it says, right? Instead of putting just plain old x in, you're going to increase your input by 2. and then you'll have, it'll do whatever the function's going to do. So just for the sake of illustration, right? I really don't know we don't know what this function is, and they're intentionally not wanting us to see that. But let's just say that f of x is equal to, I'll say, x plus 7. So in general, right, if I put something in this, right, it just takes that something I give it and it increases it by 7. So if I was to say, hey, what's f of 3? It would say, the function would say, oh, that's going to be just 3 plus 7, or the number 10, right? 3 goes into this function and it adds 7 to it, and then you get 10. Now, what if I was to say, hey, what if I was to do this f of x plus 2, right? So basically I'm saying, look, instead of taking the input you had intended to put in, I don't know if it's 3 or whatever, just increase your input by 2 units and then take that result and put that into your function, right? So instead of just putting in the value of x, right, we're going to increase that by 2, and then that's what's going to get fed into the function. So if you look at these, like if we look at A, what this is saying is, hey, your input for this function, subtract 4 from it, and then put that value into the function. So I'll just put that, subtract 4 from the input, and then evaluate the function. This next one, B, says, hey, take whatever B was, or whatever value you were intending to put in B, and take half of it, because it says 0.5 times B. So that's half of your input, and then put that into the function. So take 1/2 of your input and place that in the function. And then the final one there says, look, if you look at this is saying, hey, just put in your input, right? Your input's going to be completely unchanged. So put D in, but then after you do that, right, this represents the output of the function after D goes in. So this is the output. So after you put in D, the output's represented by f of D. So this says take your output and increase that by 12, right? So increase the output result, by 12 units. And I understand where we're going with this, and I like this question. I like that we're kind of thinking about this now, early on. But again, we've got our inputs going into the function, and we've got our outputs coming out. What's inside here is always the input of the function, right? So you can see in the first two, we're kind of tweaking the input. And then this thing right here, f of D, that represents the output, right? So what's the output? Increase the output by 12. So you can either modify your input value or modify what comes out of that by increasing by 12 at the end. Interesting.